Hi, everybody, and welcome to this recorded interview with Dr. Erin Donaghy, a brand new assistant professor. And we're catching Erin this evening on a Sunday evening in mid-December on a road trip across the country on her way to her new job. Erin, where are you this evening, and what's the weather been like today for you?
I'm in Hayes, Kansas, and today the weather's been quite nice. It's been warm, so it was real and dry, so real easy driving today.
Good,
I
good.
just left Purdue, so I came from Purdue down to across to Hayes, Kansas.
Okay, so viewers, you recognize Erin. We have featured her in a whole number of programs, both live and recorded stuff over the last 5 years. And Erin just finished at Purdue University. She was the first PhD student of Mike Eddy. And where are you going? And can we congratulate you on your new gig?
Yes, I am heading to Las Vegas, and next month I am starting as an assistant professor at UNLV.
Congratulations. Very, very exciting. I want to talk more about that towards the end of this, but I think right now I want to talk and give our viewers a chance to sink their teeth into a brand new paper by Erin Donaghy, Mike Eddy, Ken Ridgway, Ryan Eckert, Sedimentary Record of Oceanic Plateau Accretion, Revisiting the Eocene to Miocene Stratigraphy of the Northern Olympic Peninsula, Washington, USA. I'm guessing this is the first of a number of papers coming out of your dissertation. What's the main focus of this paper that I just recited?
Yeah, this is one of the chapters from my dissertation, and this one is focused on the peripheral rock sequence, which are four basin deposits that sit directly on top of our Siletzia plateau basalt. So they range from Eocene to Miocene in age. And so I'm sure a lot of the viewers know that I've been out working on the Northern Olympic Peninsula the past few summers. And so this is really the culmination of all of that work.
Well, let's do more with that, but I'm guessing another paper in another chapter was Yakutat up in Alaska. So this is just focusing on really what we were doing yesterday, Erin. I've been doing these Cascade episodes this winter, and just yesterday, episode E, I guess it was, we were learning our basics about Siletzia, the accretion of Siletzia, the timing of that. And this paper is not looking at the basalts of Siletzia, but looking at sedimentary stuff. So what you just said there, that might be a surprise to many of us. Yeah, you're looking at your cat Coco.
Yeah,
Is cat Coco can just free range in that hotel room. So
here
go
he
for it.
comes.
Oh, hey, perfect. Wow. On cue. Wow, this is like a trained animal. Excellent. Um, why are there sedimentary layers on top of Siletzia? Wasn't it in the water?
Yeah, so a lot of what I do is based in analysis, and so I use the sedimentary record to understand tectonic events. And we have these basin deposits on top of Siletzia, and they record not only just the post-accretion history, but they have this pre-sin and post-collisional history. So some of the research that we figured out during my dissertation was that these units on the peripheral have always been mapped as fork basin deposits so that they would post-date the collision of
Right.
Siletzia. But when we really start to apply these new techniques of high precision chronostratigraphy, there actually had been no prior detrital zircon geochronology done on these rocks. And then also just more traditional measuring stratigraphic sections, interpreting lithofacies, so depositional environments, and doing compositional provenance analyses, so things like sandstone petrography or conglomerate class compositions. We really started to understand that this basin record recorded pre-sin and post-collision. So those lowermost units were actually basin deposits that rode in on top of the Siletzia Plateau.
Huh.
The plateau collided to the continent, and then we have this really kind of coarse-grained unit called the Lyre Formation, which records the collision. And then as you kind of subside that oceanic plateau through time, you have development of trench slope basins, and those prograde into, or they become, they kind of transform from these isolated trench slope basins to a more integrated regional forest basin system through time as that plateau kind of subsides, and we get this influx of sediments from the continent.
It's all coming back to me now. I mean, I remember some of these discussions when I was out there with you guys a couple of years ago or whenever that was in September. And I was surprised, and I think I'm surprised again now that I'm remembering some of this stuff. You've got Siletzia before it collides. That's submarine sediments. Then it starts accreting, and those sediments, while we're accreting, were up and out of the water, I'm guessing.
Well, that's a little debated, and it's a
Okay.
difficult to tell. So that collisional history is recorded by the Lyre Formation,
Okay.
and the all of the rest of the stratigraphy, the basin deposits that are on Siletzia, they are marine. It's clear they have forams, they're turbidite deposits, but these lyres, the Lyre Formation are these really coarse-grained boulder to cobble conglomerates. And so they don't really have a lot of forams in there. If there are forams, they're very disarticulated and broken
Huh.
up. So it has been debated on and off, but most people still interpret those as proximal to medial channel deposits that would be part of these really broad, large submarine fans. So you
Okay.
do have this marine interpretation. They are mostly matrix supported, which means they've probably been transported as cohesive laminar flows. So
Hmm.
as if we think about those as debris flows, and those are pretty common in these submarine systems. So it could have been exhumed. It's likely parts of the plateau were exhumed, but most of what we see in the basin record would be marine.
Okay. Well, that's almost disappointing because I want this thing to be high and dry and this major, temporary highland where we're shedding all this stuff. We flipped the rivers inland with Mike's work a decade ago, and he's a finishing PhD student. But I'm leading to the biggest surprise, which is we start dropping the whole thing again. So we collide Siletzia, and then is this new from your work that there's a major sinking of Siletzia shortly after it accretes, and you've got a deeper basin again that's totally underwater?
Well, those rocks have always been interpreted as marine. I think what's
Okay,
new about this paper is that those rocks, their were never put into context of the collision of Siletzia because
right.
most of the previous work was done before Siletzia or the crescent basalts were interpreted as a oceanic plateau. And
Yeah.
so it's very likely that we had topographic highs that were on that plateau, and that actually caused some of this initial isolated basin deposition. And that when we did collide it, we know there was exhumation because we have this really large unconformity, regional unconformity, which separates our pre-accretion, our really distal deep marine, that's called the Aldwell Formation, which are mostly siltstones, um, and there's a nonconformity that separates those siltstones, so the pre-accretion siltstones and mudstones, from those really boulder cobble, coarse-grained conglomerates.
Yeah.
And so during that time, it was likely that we collided it, there was fold and thrust belt development, and we were able to exhume parts of not only the Siletzia Plateau, but the backstop to this collision is your Western Melange Belt.
Uh,
So we were likely, and the provenance data suggests that we are incorporating a lot of detritus from the Western Melange Belt.
yeah. Um, okay, couple things. So we were just getting into Mike's magic, really. That's overstating it, but like he shows up in central Washington. He's visiting all these sedimentary basins in interior central Washington that have been studied for decades and decades, but he has a new trick or series of tricks where he can come up with these incredibly precise dates. And that same general description is for your project as well, right? Most of those formations you've been talking about have been known for decades. They didn't know the Siletzia context, but you're also teasing out. I just saw these dates again that I'm calling them Mike Eddy dates, but I need to start calling them Erin Donaghy dates as well, where you've got this crazy precision. What are a couple of examples of things that were impossible before from your paper that you can now say, here's the precise date, we can rule out this or that?
I think what was really helpful with the chronostratigraphy was doing regional stratigraphic correlation. So a
Okay,
lot of these units outside of the Lyre formation, they're very, very similar. It's thinly interbedded siltstones and sandstones. So you're kind of on the distal to medial part of these submarine fan deposits. And so the lithology is all very similar. And so it's difficult to know the age of the rocks. But with that chronostratigraphy, we have to remember these different sedimentary sequences are all deformed. So there's a series of thrust faults, which are now vertical because of later
right,
Miocene deformation and
right.
of the Olympic core, but we interpret them as they formed initially as a series of thrust faults. And so you're separating all these very similar lithology rocks. And the chronostratigraphy is really helpful for correlating between these different structural panels or these different structural blocks. And then we can say, oh, this unit is actually the Lyre formation or the Hoko River formation, and it correlates to this unit over here, which has an entirely different lithofacies.
Hmm.
And we can start to do these really broad regional correlations that help us not only understand how depositional environments are changing through time or even spatially across the Northern Olympic Peninsula, because it's a pretty broad area. And we can also understand how the sediment provenance was changing through time. And that helps us understand when these basins were initially integrated or initially isolated and then kind of progressively filled until they were this broad integrated regional forest basin system.
Hmm. Well, in addition to a number of things that I read that paper today a couple of times, I like the way you framed it, where you guys are saying this is not the only place that we've got an oceanic plateau that is approaching a trench and getting jammed onto the continent, basically. And so this is maybe one of the first times that we've studied it with this level of detail, but I don't know what your plans are at UNLV, but like one approach would be you just start skipping around the world, going to other oceanic plateaus that have been added to continents and apply some of the same techniques. Where are a couple of other examples where it's a known oceanic plateau that used to be out in the water that's now been added to a continent?
Yeah, I think one of the most well-known examples would be on Tong Java. So like along the Solomon Arc. There's been plateaus, I believe it's pronounced Hikurangi Plateau that's colliding in New Zealand or collided with New Zealand.
Okay.
And we have the Yakutat that's colliding with southern Alaska. And I mean, there's even interpretations of the Caribbean plate being an oceanic plateau, which is collided with the northern part of South America, so Colombia, and
Huh.
even areas in Ecuador. So there are various ones throughout the geologic record. A lot of them have been Cretaceous in the past, and so there are these other records of where you can go and look at oceanic plateau collision,
Hmm.
sedimentary basins that are still sitting on top. What I think is really fun about Siletzia is that when we look at where we are in the Northern Olympic Peninsula, we're on the very edge of the Siletzia Plateau,
Right.
and the thickness of the plateau, and we know this from geophysical work in Washington, it thins to where you're only about 8 kilometers thick beneath southern Vancouver Island versus down in Oregon, the Siletzia Plateau, is between 25 and 30 kilometers thick. So
Oh.
have this really big change in thickness in just the Siletzia Plateau from north to south, and that certainly impacted its collisional style. And so even though we're looking at, this record of these basins recording this collision on Siletzia, it's really only recording this style collision in Washington. And that could be totally different in
Hmm.
Oregon. And it is totally different in Oregon because you had a much thicker plateau. And so you can even get these changes just along strike in the same oceanic plateau. So it's a really interesting problem to think about that, one plateau example might not even, it'll
Yeah,
be diaphanous, the collision, the entire plateau, and
right.
the actual collisional, so the structural styles, the basin evolution, during and after collision could be totally different on different parts of the same plateau. So it's really kind of interesting to think about then, can we really have a type example? It could be different on the same plateau, and these plateaus are
Right.
all where we have these records all over the world. So it's interesting to think about then, what are some of the diagnostic basin indicators of plateau collision or structural indicators of plateau collision, and how can we use these to pick it out in the geologic record?
God, you're good. I know, I understand why you were hired so quickly. Thank you for that. That's new for me. Somehow I missed that Siletzia Plateau is much thicker in Oregon than it is in Washington. And by the time you get up across the Strait of Juan de Fuca, the thing's down to less than 10 kilometers thick. Why is that?
I think, well, this goes back into uh, different models for the plateau formation. And so a really well accepted model for Siletzia's formation was that it was a ridge-centered oceanic plateau.
There
And
we
that
go.
spreading ridge should have been, we have a record of near trench plutons, and we know that when Siletzia collided, that spreading ridge was oriented, right beneath the southern tip of Vancouver Island. And so anything north of that spreading ridge would have been a different oceanic plate. And that would have been the plate that Yakutat was riding on. So if Siletzia and Yakutat formed as this large oceanic plateau, Siletzia would be south of that spreading ridge, and then Yakutat would be north of it. And so these thicknesses, changes in the thicknesses of the plateau could be, due to the proximity of, where was the mantle plume, because we also had the Yellowstone hotspot, how close was it to the spreading ridge? And so what's the age of the basalt on these different parts of the plateau? Like how quickly are these eruptions happening? Where are they happening? These are really large areas. So
Right.
it's not going to be a continuous. I think we like to think about plateaus as, oh, like a big, like a
Yeah.
cake, or, a big just flat layer that's homogeneous. The thickness is the same across, but really these change in thickness across its entire area. And then we saw that as well with, just topography on the surface of these plateaus. They're not razor flat. And that's how
Right.
we had these different isolated basins that before Siletzia even collided, we had hemipelagic to pelagic basins that were sitting on top of that plateau as it rode in.
Hmm.
And that just depended on the topography of the plateau, probably where it was accumulating all that pelagic or hemipelagic sediment.
Pelagic just means there's sediment raining down in the ocean water.
Yep.
Okay. Um, this is fun. Uh, I'm straying from the paper now, but I guess I want to if you allow me. Uh, does the Yakutat Plateau, in other words, the other half of the Siletzia thing, does that get thicker as you go north?
Well, so the only part of the Yakutat Plateau that we have on like at the surface is kind of the thin sliver that we have preserved in the Wrangell St. Elias area. And there, and using geophysical imaging, we know that the Yakutat, where we can image it, is very thick. It's 30 to 35 kilometers thick. So at least the part of the Yakutat Plateau that is currently colliding with southeastern Alaska right now is very thick. And that's why people believe that, the Yakutat could have also had variable thickness and most likely did.
Hmm.
And it all depends on uh, when you wanted the Yakutat to be translated
Right.
northward, and when did it first start interacting with the southern margin of South Alaska? So if it initially was interacting with the margin, in the Oligocene time, was that part of the plateau thinner so that it could actually be subducted? Because we have flat slab subduction of the Yakutat terrain all the way, it's been imaged beneath Denali. And so this is almost 600 kilometers inboard of the trench. So there's flat slab subduction of this oceanic plateau. And then people believe that when the thickest part of the plateau started to interact with the trench, it jammed the trench.
Huh.
It's getting caught. And now it can't really fit well beneath the trench anymore. And so it's jamming the subduction zone. And that's the thickest part of the plateau that's now getting caught up as it's being subducted.
Okay, well, that's cool because in the next few letters of this series, we're going to finish clogging the trench with Siletzia and we're going to start up the Cascade Volcanic Arc 46 million years ago, I guess, outboard of the big thing that clogged the trench. There's maybe a future volcanic arc south of where the Yakutat is clogging things currently. I don't know. It's fun to go back and forth, I guess, between present day up there, like a modern example. I knew Yakutat is still getting jammed, but to project to the future, I mean, that's kind of a dumb thing to have you comment on, but like it's fun to think about that we're seeing in Southeast Alaska in general the chronology and the drama of what was happening, 50 million years ago down here, which I'm sure is the point of parts of the current paper and then the next one as well.
Yeah.
Any comments on that? I don't know.
Yeah, I
I'm,
mean,
I'm,
the idea would be that you would have to renew subduction outboard of, wherever the Yakutat's going to break off, or that subduction zone will eventually have to be translated. But where that's happening is
yeah.
there is research on it, but
Okay.
Siletzia's collision's totally different, right? Because we have outboard migration or renewed subduction, again, outboard of that accreted fragment of Siletzia pretty quickly. So depending on when you want Yakutat to start interacting with the margin of southern Alaska, that collision has been going on for much longer period of time than versus Siletzia collided and then probably, we have
Oh,
cascades being initiated by 46 MA. It's a much quicker transition. And that's where you can start to think of, well, the rheology of this plateau must have been different then. Siletzia was being collided when it was really young, when it was
yeah.
still being formed. And so if it's really hot and buoyant, it might behave really weak. And that might have allowed for slab break off to occur pretty quickly. And then outboard migration of our new subduction zone. On the outboard side of Siletzia versus Yakutat, that hasn't happened yet, right? We've been having flat slab subduction, and that's why we have the incredible topography of the Wrangell St. Elias range
Hmm.
sitting right on the Gulf of Alaska.
Hmm.
So that the Yakutat, flat slab subduction of the Yakutat is a major player for some of that topography that's being created.
I could go on forever. This is great. I keep feeling like I want to go to the next topic, but you keep saying really interesting stuff here. I think I do want to go. I want to do two more things if you have a few more minutes before you hit. You're probably exhausted. You've been driving since sunrise this morning or even earlier, maybe?
Yeah,
Okay.
yeah, it
All
was
right.
like an 11-hour day.
Oh God. Okay. Yeah. Give me if you
Not too
got
bad.
10 if you got 10 more minutes, let's do it.
Yeah.
Let's do two more things. You may not want to play this game, but I think I want to play a little game with you because you're the expert and just confirming or denying a few things I tried to do yesterday with the live stream series. And then I've got a few days before the next episode, and I might want to ask a little advice about how I might approach the next couple of letters. And then I want to talk about your immediate future and what you know and what you are hoping to do, at least in your first couple of years in Vegas. Um, okay, so this can be quick and you can pass if you've got good stuff that you haven't published yet and you don't want to reveal whatever. Um, yes or no, the Yellowstone mantle plume is part of building Siletzia.
Well, my research didn't, tackle that in
Yep.
particular. It was an initial goal, but then, moved on to kind of focusing more on the Basin record. But uh, most of, or probably some of the more well-accepted models for construction of oceanic plateaus generally have a oceanic or a mantle plume involved in the construction of these plateaus. So the Yellowstone hotspot playing a role seems like a pretty good candidate to me that it was there. And you've mentioned this already, it looks like a very similar geometry to Iceland, where you have the Iceland hotspot and it's sitting right off of the spreading ridge, and Iceland is forming over top of that spreading ridge with that hotspot sitting kind of right next door.
Thank you. Uh, so everyone is agreeing, or at least I'm talking to you. You're agreeing that we need a spreading ridge in addition to a mantle plume for Siletzia.
Yes, we know the spreading ridge was there based on the near trench plutons and geochemistry, so like adikites that are present all along Washington, Vancouver Island, and Oregon. And so we know the spreading ridge was there. We know it was at the southern tip of Vancouver Island, right at 50 MA. And so I would say, yes, the spreading ridge has to play a role in the construction of Siletzia. And that's what makes Yakutat kind of being that northern conjugate to the Siletzia Plateau such a good candidate.
Okay. Was Siletzia slash Yakutat, when it was on that spreading ridge, was it moving towards North America, or did we sideswipe the whole thing? Or did we plow into the whole thing? Or both?
Um, I mean, so with the spreading ridge, you can have, as you subduct a spreading ridge, there's transform segments. So that's how you get ridge jumps. But this, the collision of Siletzia and Yakutat was both very diachronous. And I think that's because the shape of these plateaus, we don't necessarily know the shape of the Yakutat and the Siletzia plateau, but we know that the timing of collision was different with the Yakutat and the Siletzia
Yeah.
plateaus. So this was occurring, and that's probably why you see the range of, 53 MA to 48 MA. And it's not because we don't know, but there's evidence for it occurring at different times along the continental margin. And so even though you have this and it depends on, how you believe these plateaus might grow, but sometimes models have them growing almost, and this is in the Ray Wells paper as well, but almost as a V-shaped pattern from
Right.
the spreading ridge. And so then you have one, depending on the orientation of the spreading ridge, and then depending how these different fragments of the plateau are growing, and then how many, ridge transforms there might be. You could still have North America coming towards this plateau, but the collision, just depending on the shape, would have been, very diachronous along the
Mm.
continental margin. But the strike slip, we really have strong evidence for acceleration of strike slip. So like if it was being sideswiped, that's kind of post 50 MA. So we see that switch kind of from more accretionary tectonics or collisional tectonics to strike slip tectonics after 50 MA. So I would say, yeah, this thing was probably coming on head on, but it's just diachronous because of the shape of the plateau and
Mm.
probably the orientation of the spreading ridge.
Couple more with there, and then we'll transition to Vegas. Do you have strong opinions on the names of the ocean plates, uh, pre-accretion, during accretion, after accretion? Is there a major change in the ocean plate maps? Do you have maps in your dissertation or a paper that's about to come out? Like I'd like to, was doing that all late summer with Mike and Basil and all these folks, and we had a little bit of consensus, but we also had some major changes between research people, like resurrection plate, Kula. How have you dealt with that? Are you still kind of thinking resurrection Kula doesn't really make a difference for your work?
Yeah, for my work, it doesn't it doesn't, there's not really too much of an impact because you could have the resurrection plate as long as that thing is fully subducted by 50 MA, because then
Yeah.
we have to start moving things up the margin, along the margin after 50 MA. So if there is a resurrection plate, then it could certainly be there, but it has to be fully subducted before you start having this large scale translation, regional scale translation of these different terrains along the continental margin. So
Mm.
we do have a paper that's in review, which is covering kind of the Yakutat, Siletzia, collisional history, and that's in review right now. And so I have one figure that kind of has plate configurations on there, but I've left it pretty vague and said
Okay.
Kula or Resurrection plate because it doesn't play so much of a role for getting the Yakutat up to Southern Alaska, as long as the resurrection plate is out of the picture, post 50 MA.
Well, yeah, I'm starting to realize that I guess I'm obsessing about something that's not that important. Kula versus resurrection. I don't know if that's such a crucial thing to figure out for, I just want to start the Cascades and have set the table for that. But I don't know. It's more important to have that spreading ridge, I think. And then Jeff Tepper's chronology of getting that Cascadia trench set up in a particular way. So maybe I'm don't need to go there. So the advice I'm asking for, Erin, is, I mean, you're going to be teaching some classes as soon as January. Are you guys on quarters or semesters?
They're on semesters. I am on a teaching release next semester, so I will not be
Okay.
teaching next semester, but
Okay.
likely in the fall.
You will likely in the fall. So I guess I'm currently trying to decide in the next letter, do I go right to the ocean plates and try to nail that down, knowing that a couple letters later we're going to start the Cascade volcanic arc, Jeff Tepper's break off and his whole story there, or is the next letter just kind of almost going historical, meaning just introduce, just go, this is this formation over here, and this is the I don't even know the names of the things, like Tianaway, I guess, and Silver Pass volcanics, and maybe I jump out to the peninsula and introduce a few of your formations and just try to collect a bunch of data from sedimentary basins and volcaniclastic units and other things, and then wait for the next letter to say, or maybe two letters from then, and say, remember all that stratigraphy we've been learning? That was, people were just collecting that information for the last 50 years, and now we have a new way to interpret it. I think I'm more excited about the second now that I just have said it out loud. Any thoughts there about the pros and cons of going to the ocean plates right now, since we just introduced Siletzia, or wait a couple letters?
You could probably wait a couple letters. I think if you're gonna like go, if you have to go back to it anyway, then when you start to really get into the Cascade arc, then maybe it's just better to kind of introduce it right before, and remind everyone the different models of where the spreading ridge might have been, and where it was and what time that was, and then what oceanic plates could possibly be involved. But uh,
Yeah.
I think it would be fun to hear about all the different formations as well, the different units, and that can be linked into those models, or you can just kind of save that for later. But yeah.
Or even just do an inventory. Like, I've always heard about some of these formations. I don't know anything about them. I don't know which ones could be the same thing, which is basically circling back to what you've been doing, these regional correlations. Like, let's do that. Were there three formations that were viewed completely independently on the Olympic Peninsula until you and Mike came in and said, hey, this is all the same stuff? We've got exactly the same ages out of these units. Is it that simple, where you are regionally correlating and saying these are not four different units, it's all the same stuff? or not quite?
No, so we kept the units the same. What was really helpful with the chronostratigraphy was that some things that might have been mapped as another unit, we were like, oh, wait, this is just a different facies of this unit based on, we dated this interbedded tuff. And so this actually correlates with the Hoko River formation, and it's not this other unit. It's
Hmm.
it's not the I think a lot of our interpretations were the only thing we really, really changed was things that might have been mapped as the Blue Mountain formation
Oh
before,
yeah,
or the
right,
Blue Mountain unit,
right.
the Hoko River formation. And so the chronostratigraphy really helped us figure out these units because, like I said, they have very similar lithologies and lithofacies. And so the H data was really helpful in kind of determining which unit was which. Um,
Okay, let's transition to the last little part of this interview. You've landed this new position. What did you learn? What skills did you acquire by working with Mike Eddy that you didn't have before? You were a Paul Umhofer student at Northern Arizona. I'm guessing that was primarily a sedimentary basin type project in the Chumstick. Then you did some work, I believe, in the oil patch. What did you get from working with Mike at Purdue, and how, and are you therefore doing very similar? So I think of Mike as someone who can do so many different kinds of things in the field, in the lab, structure, sedimentology, tectonics, igneous rocks. Are you very similar now? Have you learned all these things from Mike, or how do you view yourself a little differently than Mike Eddy at Purdue University in current form?
Yeah, I think uh, what I really learned, so my work with Paul Umhofer was very focused on sedimentary basins. And so if you ever go back to either, I mean, it's mostly in the master's thesis, but it was really detailed sedimentology. So really detailed lithofacies and lithofacies descriptions. And these are the sedimentologic processes that are forming these different bed forms. And that means, because of the sequence of bed forms that we see, it's this depositional environment. And so it was really this, putting together this basin story, but from a depositional environment and sediment provenance perspective. And while I got to learn a little bit of tectonics, I really didn't, dive into it 100%. And so one of the things really learned from Mike and Ken was, really diving into these tectonic processes. So things
Hmm.
like oceanic plateau collision and thinking about the rheology of plateaus and how that would, impact structure. And then of course, I learned a whole new technique in zircon geochronology. And so I had never done that level of detailed lab work. So that was entirely new and fun, and I love it and I miss it.
Ha.
Um, so I definitely learned a lot more of, here's the basin story, but now what can this tell us way more about the tectonic processes and actually thinking about tectonic processes or the rates of those processes and how that is related to the rates of these sedimentologic processes we're seeing. So how does the basin really record these tectonic events on a detailed level? So I never really thought, even working with Paul Umhofer, how these large regional strike slip systems work, because I was just, it was a small master's project and so focused in on the sedimentology and basins that
Yeah.
I think at Purdue, what was really nice is learning all these new techniques and then how can we really use this basin record? So the sedimentology that I kind of knew already, but let's really think large scale tectonics. And so that's really, one of the key things that I took away and learned was way, way more about structure and tectonics. And of course, I learned a lot more about petrology and volcanic and igneous
Yeah.
rocks as well, because those were never part of my master's thesis at all. I'd always been kind of purely a sedimentary rock person, but worked with a lot more volcanics, volcaniclastic rocks, and igneous rocks in my PhD. So it was far more integrative.
That's it. So integrative. That's what I think I'm impressed by the most with Mike Eddy and now you. It's just so many different skills that are working together and you're not reinventing or you're not starting from scratch. You're using all these prior studies and all these maps from the last 70, 100 years and then revisiting the stratigraphy with these new techniques. It's so exciting. Finally, what do you know about your new job? What are you hoping to teach? And do you have a plan for research with some of your students in the next few years? And where might that be working? Or where might you be going in the field if things work out?
Yeah, so I will be teaching sedimentology and field camp and field methods. So,
Nice.
right up my alley.
Yeah.
Very excited about that. And I am looking for graduate students to start in the fall. And I am planning on going out to Washington this summer, hopefully with those students, but out to
Really?
the Olympic Peninsula again. But really, this is another chapter of my thesis, which is in prep for to be submitted to a journal. But I haven't really talked about it a lot. But I did a large portion of my PhD thesis working on the Blue Mountain unit, and I worked
Yeah.
on this with Nick Regier, who was an undergrad at Purdue at the time, and so that was kind of his undergraduate thesis project. But we were looking at the Blue Mountain unit, which had always been interpreted as interbedded with the lower part of the crescent formation until Mike, during his PhD thesis, he did detrital zircon geochronology on those rocks. And then from the looking at the youngest population of zircon ages there, was able to tell that no, these interbedded sedimentary, or they're not interbedded, these sedimentary rocks are much younger than the
Yeah.
basalts. And so that means they have to be structurally juxtaposed against the crescent basalts. And so part of my work was to go up and do lithofacies mapping and to look at that unit in more detail. And we interpret it as part of the Olympic core. So it's part of that subduction complex and it would be the oldest part of the subduction complex. And so I would
Hmm.
really like, and my plan is to get some students started working on some of the subduction complex rocks. So things like the Needles Gray Wolf and the Elwha, and doing the same kind of detailed lithofacies mapping to understand the record of accretion and how that, relates. We've accreted Siletzia now, and now how are we building the subduction complex after we've accreted this oceanic plateau, and while we're forming our forearc basin at the same time. So what's happening in the subduction complex now? Because all of these things are related. You have your arc, your forearc basin, and your subduction complex. So now let's
Right.
look at the record in the subduction complex. And so my goal is to get a student working on that. Hopefully, we can go do some preliminary reconnaissance work this summer and then get another student working on some of the other Eocene sedimentary basin deposits in southern Washington.
In Southern Washington. I was
Yeah.
hoping you were going to say this. You might have two different students working up here in Washington, two different projects potentially in the next couple of years, as soon as this summer, or at least one of them this summer. Oh, I'm so thrilled. I'd love to meet up with you. I don't know when you're planning, if come on. I'd love to showcase your work. Let's just keep this going, Erin. Like this has been a nice relationship we've had, and I hope that I can help with attracting some good students. I don't know. When so is there a deadline for people applying to work with you this winter?
Yes, it is January 15th is UNLV's program deadline for graduate applications.
Okay, well, maybe this video will get into a couple people's hands that didn't know about you and they'll try to apply. Maybe you've already got plenty of applicants. I don't know, but like it'd be really exciting to see more of this work. And it sounds like that's the plan. So that's great. Any final thoughts from you about the new paper or another paper coming or anything else you'd like to add before I let you guys hit the sack tonight?
No, I think like I have some papers in review and I'm hoping to get that other chapter submitted next year, early
Okay,
next year. It's kind of like next on my docket to finalize and get submitted pretty soon and I can present it at the Cordillera Conference in Sacramento
good.
this spring. So I'm excited about that because I haven't presented this chapter yet. So it'll
Okay.
be a lot of fun. And yeah, I think there's a lot coming from my way and yeah, I'm excited to do more at UNLV.
Are there other brand new professors showing up with you?
Yes, it was part of a cluster hire. So there will and some have already started. So there was a new structural geologist hired and an economic geologist hired. So uh,
Excellent.
yeah,
Okay. Well, please hold the line. I'm just going to stop this and we can chat for just a couple more minutes. But
yeah,
thank you, Erin Donaghy, for your time tonight. I'm so glad that you emailed me about this new paper, and it's really fun to just catch you cross country. So thank you so much, Erin.
yeah.